Hi everyone, welcome to the second video on ribbon homology cobordisms, in which I will talk about applications that one could get from the main theorems that I stated in the part one of this talk, which is a joint project with Ali Akbar Dayami, Ty Littman, and Shay Velovic. So let's recall first from part one, the main theorem. So if you have a ribbon or homology cobordism from y minus y plus, then we prove that the Thurston geometries of y minus and y plus satisfy a hierarchy, in that you cannot have certain geometries going, you cannot have a cobordism from a certain geometry to another geometry. You cannot, for example, go from nil geometry to spherical geometry. We also proved that the dimension of the G representation or character variety of y minus is at most that of y plus. And we also prove that the instanton fluid homology and Heegard fluid homology of y minus and y plus satisfy the condition that the cobordism maps associated to W are injective. For a technical reason, that the Heegard-Fleur statement works only for ribbon Z-mod 2 homology cobordism, whereas the other statements work for Q homology cobordisms, which are more general. I want to also point out here that we prove something stronger than the statement written here about G representation varieties. We actually show the following. If you have an irreducible G representation of y minus, where G is a connected compact Lie group, then you can extend the representation to pi1 of W to the cobordism, which then restricts to the pi1 of y plus to get a G representation of the pi1 of y plus, which, and this process gives you a map on the level of varieties from the pi1 of y minus to the pi1, from the representation variety of y minus to the representation variety of y plus. So just to mention, we also prove analogous results for various flavors of instanton and Heegard fluid homology. But some of these require conditions to make sense. And for some of these, we prove the weaker conclusion that the invariant for y minus is isomorphic to some manner of the invariant for y plus. So now in this talk, I will give 3 different applications of the main theorem stated here. And without further ado, here is the first application. Recall that the exterior of a strongly homotopy ribbon concordance is a ribbon homology cobordism from the exterior of negative nk minus to the exterior of the positive nk plus. So our theorem states that there are no strongly homotopy ribbon concordances from composite knots to small knots. So one way to think about this is that small knots have fundamental groups associated to their exteriors being small, so to speak. And composite knots have sort of larger pi1s associated. And so you cannot go from a larger pi1 to a smaller pi1 under a ribbon homology cobordism. That's the idea. And we prove this by considering, I should first mention that a small knot, K, is exactly a knot whose exterior does not have a closed non-boundary parallel incompressible surface. So we're going to prove this statement by considering G representation, the G representation variety of the exteriors y minus and y plus of the knots K minus and K plus. And the proof goes as follows. So given any knot in S3, Sivak and Sentner proved that there exists a one parameter family of irreducible representations into S of the exterior of the knot group into SU2. So obviously we're going to take G to be SU2 here. You can think of this result by Sivak-Sentner as a strengthening of the Kronheimer-Rufka results that says that there exists an irreducible representation into SU2. In fact, so Kronheimer-Rufka proved this by using instanton flow homology, and in fact, Sivak and Sentner's proof uses a perturbed Chern-Simons function. So you sort of perturb the Chern-Simons function for instanton flow homology, roughly speaking, you get this result. Now, if you have a composite knot, you can take the irreducible SU2 representations for one of its subends, and then take the other subend, and you use conjugation to get a two-parameter family of irreducible representations into SU2. So, and in fact, you can further conjugate this with SU2 to get that the SU2 character variety of K plus of K minus, because K minus is a composite knot, have dimension greater than or equal to 2. So again, what this means is that if you have the character variety is you can think of it as the representation variety modulo conjugation, right? So you sort of, if you have a two-parameter family of irreducible representations, then if they're all, if you conjugate them further, then you can do this. You can get the result for character varieties. So the character varieties have dimension greater than or equal to 2. In other words, the SU2 representation varieties of K minus have dimension at least 5, because the difference in the dimensions of these two things, representation and character varieties, is 3. So you just add 3. But our theorem up there says that K plus must have a representation, SU2 representation variety that is also of dimension at least 5. And then you can go back down again to character varieties to see that the SU2 character varieties of K plus must have dimension at least 2. But then that is by a result of Classen. That means that the knots K plus cannot be small. So that's a contradiction. For the experts, the reason that we don't just use character varieties and go directly from character varieties to character varieties is a little bit subtle, because it really depends on what you mean by dimension of a character variety. First of all, I want to just mention for topologists, the dimension of a variety here is basically the highest dimension of each of its components. So if you have x, y equals 0, this variety, then its dimension, we think of that dimension as 1. Even though the tangent space, we'll come back to that, the Zariski tangent space as the origin for this variety has dimension 2 instead of 1. And to complicate matters, the character variety is not really a variety, it's really a stack. And so it's easier in this case for the proof to go through the variety map, the map of varieties. So here's a second application. We're going to focus on Seifert-fibered homology spheres. That means that means Z homology spheres in particular. So here y minus and y plus are both Seifert-fibered Z homology spheres with n and m exceptional fibers, respectively. So suppose that there exists a ribbon Q homology cobordism from y minus to y plus. Then we prove that the Casson invariant of y minus is less than that of y plus in absolute value. We prove that y minus and y plus both bound negative definite plumbings or both bound positive definite plumbings. And finally, we prove that the number of exceptional fibers in y minus is at most that of that in y plus. So how are we going to prove this? We're going to prove it using both the representational character variety statement and also the Floer homology statements. So we're going to go down the list. So first, look at the Casson invariance of y minus and y plus. And we can prove this by using either of the Floer homology statements, Instanton or Hegat-Floer statements. The astute audience member might realize that, well, what about for Hegat-Floer homology, you need Z mod 2 homology cobordisms, whereas in our theorem you have the more general Q homology cobordisms. But in fact, that's not an issue because of the fact that Q homology cobordisms, ribbon Q homology cobordisms between Z homology spheres are all ribbon Z homology cobordisms. So you can either use Instanton or Hegat-Floer homology, and the proof is simple. You take the Euler characteristic of I sharp or HF hat, and you get the Casson invariant. Of course, you should see that they all lie in the same mass of grading, homological grading. So then the second statement on y minus and y plus, both bounding negative definite or positive definite plumbings, is just a statement that again the Floer homologies lie in the same homological grading, which determines the sign of the Casson invariant lambda, and which also determines whether they bound negative definite plumbings or positive definite plumbings. So the point is that our maps I sharp of W and F of W, they respect the homological grading, and so we get this immediately. And finally, we have a statement on the number of exceptional fibers, N and M. So there's not going to be a slide for this, but I want to go into this with just a brief description of what's going on. So we're going to prove this using the G character variety. So in fact, our statement on the G character variety is not, we sort of avoided talking about maps of stacks and that kind of stuff. So instead, what we prove is that if you have, remember that you have a irreducible representation for y minus, that gives you an irreducible representation of y plus. And if you compare the Zariski tangent spaces to the character varieties at these two irreducible representations, or rather the conjugacy classes associated, then the y minus one has a smaller dimension than the y plus one. So the trick here is that Fintushel and Stern proved that for a Seifert fibered homology sphere, the Zariski tangent spaces have dimensions 2t minus 6, where t is an integer smaller than n. So what we prove is, what we do is that we just prove that it for y minus or y plus for Seifert fibered homology spheres, you always have an irreducible representation that has the maximal possible dimension in the Zariski. Sorry, you always have a representation with the maximal Zariski tangent space dimension, which is 2n minus 6. Well, that immediately, given our statement on the Zariski tangent space dimensions, that immediately tells us that y plus also has an irreducible representation with character, whose Zariski tangent space has 2n minus 6. Well, that means that its number of exceptional fibers must be at least these n. So having proven this statement, there's a very fast, quick corollary we can get, which is that if you have two Montesinos knots with determinant equal to 1 inside S3, such that the number of rational tangles in the minus side with denominator at most 2 is larger than that for the plus side, then there are no strongly homotopy ribbon concordances from K minus to K plus. The proof is very simple. You just take the branch double cover, and what you get is a cipher-fibered homology sphere, and the number of exceptional fibers in the cipher-fibered homology spheres is exactly the number of rational tangles with denominator at most 2. So you get that for free. Okay, so on to our last application in this talk, which I really like because it doesn't seem to have any on the surface, doesn't seem to relate to ribbon homology cobordisms at all. This is also the theorem that I mentioned in part 1 of this talk. Again, the theorem is that if you have an irreducible Q homology sphere Y with a null homotopic knot K in Y, such that the zero surgery on Y along K has an S1 cross S2 summand in it, then N is basically just Y, is orientation preserving homeomorphic to Y. I mentioned in part 1 of the talk that this also works for L, links L, no homotopic links, but then the statement will have a little L here, that's the number of components of the link L. So how does ribbon homology cobordisms come into this? So let's dive into the proof. The idea is that you actually can build a very natural ribbon Z homology cobordisms from N to Y. So we do the following. So we're actually going to first build a cobordism from Y to N, the other way around. So you take Y, you attach a 2-handle along K with 0 framing. That gives you the 0 surgery on Y along K, of course, on the other end, and by assumption, by the hypothesis that's N connects some S1 cross S2. Now you have this S1 cross S2 summand in it, and you can add a 3-handle along the S2, some points cross N S2 inside the S1 cross S2 summand, and you get to N. Just capped off the S1 cross S2 part. So now if you invert this, that's going to be a cobordism from N to Y. Instead of having a 2-handle and a 3-handle, you have a 1 and a 2-handle. So invert it, you get a ribbon cobordism. You can check very easily that this is indeed a Z homology cobordism. So it's a ribbon Z homology cobordism, and all the theorems that we stated earlier apply to this. So now I'm going to call this cobordism from N to Y W. Now the first claim is that W retracts to Y. So let's see why that is true. So you first look at the 2 handles that you're attached. Well, K is null homotopic, so you can homotope K to a point, and so attaching, the 2 handles can be retracted because of that. And now you want to check that the 3 handles can also be retracted. Sorry, I keep using the plural here because this also, as I mentioned, this works for links L as well, and you can imagine that the proof goes in the same way. For the 3 handles, so you want to see that those 3 handles also retract, but then Y is irreducible by assumption. Because Y is irreducible, there's no pi 2. So that means that you can retract the three handles as well. So now we have a retraction from W to Y. Now, coming back to this ribbon Z homology cobordism that we built, from Cameron-Gordon's theorem in part 1, we see that there is the maps on the fundamental groups from N into W and from Y into W. The first one is injective and the second one is surjective. But then we just said that W retracts to Y, right? So the inclusion map from Y to W into W must be injective on pi 1, right? So that is actually an isomorphism. Now, what that also means that is that rho, the retraction from W to Y, is also an isomorphism on pi 1. And in particular, you get a map from pi 1 of N to pi 1 of Y by doing the inclusion and then the retraction map. And that map is, by this diagram, is going to be injective. And well, I claim that it's actually surjective as well, because what you have there is actually a you can look at the H3, H lower 3, the third homology groups of these manifolds, and recall that this is a homology cobordism, Z homology cobordism. So they are all isomorphic. So that map that I just mentioned actually sends the fundamental class of N to the fundamental class of Y, which means that it is a degree 1 map. And if you have a degree 1 map, then it must be surjective on pi 1, because if not, then you can take the image and take the cover associated to that image in pi 1 of Y, and then you see that because the covering is non-trivial, you see that the degree of the map inclusion followed by retraction is not a degree 1 map. That's a contradiction. Well, if it's a degree 1 map, then it's surjective, and so it's surjective on pi 1. And so you see that the first map is also an isomorphism, which means that pi 1 of N and pi 1 of Y are isomorphic. That's almost done, right? Like, we're almost done. So N is homeomorphic to Y. If 2, 3 manifolds have the same fundamental groups, then they are homeomorphic unless there's length spaces. But then that's okay, because for length spaces, that's okay too, because recall that N and Y are Z homology cobordant, and Z homology cobordant length spaces are homeomorphic. Now, notice that I never said anything about orientation preserving homeomorphic here. I just proved that just now. We just proved that they are homeomorphic. So in order to see that they're orientation homeomorphic, you have to work a little bit harder. I didn't write it down here, but basically, what you do is that the degree 1 map I mentioned earlier is actually orientation preserving. So if N and Y are aspherical, then you're done by the Borel conjecture. And if they're not aspherical, if they're length spaces, then you just need to know that Z homology cobordant length spaces are actually orientation preserving homeomorphic. So that's okay as well. And finally, you need to deal with spherical manifolds that are not length spaces. So what we do there is we have another argument that involves taking covers of these of N and Y and W upstairs, and eventually you get back to length spaces and you use the same statement, sort of the same kind of statement as before, and you're done. So that is the end of my 2-video talk here, and thank you very much for listening to all this, and I'll see you guys very soon. Thank you.